Hi, very good afternoon to everyone. Hi everyone. I can see many of you have already arrived. So I can see Teo Yiqi, Yici, and also I can see Hu Heng Dong. I can see Soyan Chang. Besides, I also see many of you have already attended. Xie also here. Han Xiang, Heng Dong, Xin Shen, Junwei, Gashing, Maylin, Wenliang, Xue Wen, and also Yihang, Isi, and Yan Chang. So good afternoon to everyone. So basically, this is the first tutorial session that we are having. And now is the Chinese New Year Eve. So I wish everyone Chinese New Year, Happy Chinese New Year. So without further ado, I would like to start our tutorial sessions. So basically, what we are going to do today is to do the tutorial number 1. Okay. So the tutorial number 1, we already done the question 1 and 2. So during our lecture class. So today I want you to continue to do the question number 3. So for this question number 3, I believe you all already have the tutorial sheet. So all these question 3 until the question 7 that we are going to do today. For your information, we are going to do 5 questions today, but mostly I will give you the answers, so don't worry. So for the question number 3, we are going to use the M-STAR's law. Okay, what is this M-STAR law? Okay, M-STAR law means it will be using these 2 formulas, but particularly the most important formula is actually the speed up. What is the speed up over here? Okay, the speed up formula, okay, speed up overall is equivalent to the old execution time over the new execution time. Okay, and then is equals to 1 over 1 minus the fractions of the enhanced portion plus the fraction of the enhanced versus the speed up of the enhanced. Okay, so this will be the formula that we are going to deal with for the first 3 questions. So without further ado, let me ask if anyone has any question. Anyone has any question, you can raise your mic. Okay, you can turn on your mic and then you can talk to the microphone. So I hope you are not having your reunion lunch now. So if yes, then never mind, you can have it together with your class. I don't mind one. So any question you have before we start our tutorial? Okay, if no question, then I'm going to start, yeah? So basically, for today, let me see whether I have already recorded or not, because yeah, I'm afraid some of you might not be able to join today. Okay, so the first question. So this will be the first question. Question number 3. Suppose that we want to enhance the processor for the use for the web serving. The new processor is 10 times faster on computation. Okay, they want to use a new processor in the web serving application than the original processor. Assuming that the original processor is PC with computational 40% of the time, and it's waiting for the input-output 60% of the time. Okay, so input-output you cannot improve, but for this 40%, you are able to improve it for 10 times faster. So what is the overall speed gain? Okay, speed up gain by incorporating the enhancement. Okay, so this will be the formula that we want to use. What is speed up? The speed up actually depends on the portions of that your enhancement, your new processor can improve, right? So let's say your new processor can improve for 10 times, only for the 40%. So remaining 60% of the time, so you cannot improve it. So use this formula. Okay, let me make it a little bit smaller. So the speed up equals to 1 over enhanced. So what is the fraction here? Anyone can tell me what is the fraction? You can turn on your mic and tell me because yeah, there are not much people here. You can just turn on your mic. Anyone talking? No, Okay, so let me, not then I will, if you have any answer, you just let me know, yeah? So speed up equals to 1 minus 0.4. The portion that you can enhance divided by how many times you can enhance. So if you use this formula, you will be able to get 1.56. So you have the 56% better performance, better speed than your original processor under this condition. Okay, your 10 times faster can only be applied to the 40% of the time, whereas the 60% of the I/O time, you cannot enhance them. This is say 60%. So any question? I would like you to have 5 minutes to ask me any question if you have. Any question? Okay, if
So
there's
far, no.
so far no, yeah, who is talking? Yeah, may I know who is talking just
Yeah,
now? Who was
Chia
talking?
here.
Yeah, Chia, hi.
Because
Yeah,
this
thank you for
question 3 and 4, I think sir already discussed during the lecture, so I think shouldn't be a problem now.
Oh, okay, sure. Yeah, thank you for telling me this. So you just as a revision first. Okay, thank you, Chia. So 3 and 4 we already finished. So today we are going to check question number 4 also finished. So let me brief you a little bit. It's a bit the same thing. So we will still use the same formula. 1 minus the fractions that can be enhanced. And the fraction can be enhanced divided by how many times it can be enhanced. Okay, so same thing happens here. So since we already finished, so we are going to the question number 5 directly. So we will a bit faster for today. So for question number 5, you have a system that contains a special processor for doing floating point operations. You have determined that 60% of your computations can use the floating point processor. Okay, 60% only. You will have the improvement. So the speed up is 40% faster. Okay, when it does than when it doesn't use it. So the overall speed up is still using the same formula. The speed up equals to 1 over 1 minus the portion that can be speed up plus the portion that can be speed up, which is 0.6 divided by 140%. Because you have 40% faster. Okay? Yeah. So eventually you will get 1.206. So this will be your question number A. So for those who want to look at this, let me actually upload the answers. At the same time, you can look at it at your computer, tutorial 1 solution, so that it will be faster for you to learn. But if you want to do it first, it's up to you. So you can do it first, then only we will, then only you see, look at the questions. Okay, let me upload, yeah. Where's my okay, solution tutorial number 1. Okay, so I will upload. For those who want to study at home, then it's fine. So I will post it. As you can see, I already posted it. So you can actually look at the solution at your own free time. So now, for the question number B, okay, in order to improve the speed up, that you are considering 2 options. Option 1, modifying the compilers. There are 2 options here. First, you use the compiler. Another one, you use the design of the new processor. So the option 1, modifying the compiler so that 7% of the computations can use the floating point. Okay, can use the floating point. So you modify the compiler so that 70% of the computation can use floating point processor. Means you can have 40% faster when you do this. So as a result, so you can have more portions that can be enhanced, right? From the 60% to the 70%. But the cost of this option now, because you need to hire a very good compiler writer, so the compiler has to be designed right. It will cost you $50,000. Okay. Whereas for the option number 2, you can modify the floating point processor. This one even tougher. Yeah. So the speed up of the floating point processor is 100% faster compared to 40% faster when it doesn't use it. Okay, assume in this case that 50% of the computations can use the floating point processor. So 50%, meaning that from 60 now you come back to 50 or even lower. So, but at this option, number 2, the cost of this option is 60,000. So which option would you recommend? Justify your answer quantitatively. Okay, so do you want to do or you want me to show you answer, Chie? Chie, are you still there?
Yes, yes.
So I will show you the answer, yeah? Okay,
Yeah.
so there's 2 options. First option, you improve the floating point instructions to 70%. And then the speed up remain 1.4, where you use a good compiler. For the second case, you design the redesign microprocessor. Then your floating point operations drop to 50% only. Okay, because of some limitations, so they cannot use the floating point instructions. Instead, they have to use a normal integer instruction or whatever, okay, to do the floating point operations. And then for the speed, it has been increased by 100%, means it can be 2 here. So the overall speed up for the first case, so you use the M star equations, so you get the 1.25. Okay, so the cost per the speed up, because the speed up is 1.25, so your cost is $50,000. So for one speed up, you need to spend 40,000 for the option 1. Whereas for the second speed up, it will take you 1.33. You can do the 1.33 speed up, but the cost per speed up is 45,100. Okay, dollars. So this is option 2. Therefore, the option 1 is better because it has a smaller cost over speed up ratio. So this is the answer. So I will give you like 5 minutes to have a look at these answers. If you have any question, you can let me know. Yeah. So the M star source equation is very, very important because in order to calculate the times, how many times that you can speed up the computer using a particular number of instructions is given by this formula. So after you have done this for many times, then you will be very, very familiar with these equations. Okay, if no question, then I will continue, yeah. Question number 6. Okay, let's come to question number 6. Let me see whether you have any question. No question, huh? Yeah. So now, question number 6 is about supposing that you have a load and store computer with the following instruction mix. So you have a lot of instructions. So these are the instructions. You have the ALU operations like addition, subtraction, multiplication, and also the division. So this take up 35% of your instruction. Each of these instructions span about 1 clock cycles. Because it's a quite simple one, you just need to design a ALU, arithmetic logic unit, that directly do the calculations. And then for the load instruction, there is a 25% of them. Then it uses 2 clock cycles. So it means you need 2 clock cycles to do 1 instructions. Now the third one stores, they use 2 clock cycles, but it take up 15% of the frequency of inside your instructions. And the last one will be branches. It takes up the most clock cycle, which is 3 clock cycles. So the frequency of using the branch instruction is actually 25%. So totally how many? 35, 25, 60, 15, 25, 100, right? So total is 100%. So the whole program only use these 4 types of operations. Yeah. Now compute the CPI. So what is the CPI over here? Okay. What's the CPI? Okay, the CPI is given by this formula. Compute the CPI, clock cycles per instruction. So you have to get the average clock cycle because some instruction has 1, some instruction has 2, and then some instruction has 3, right? So you definitely have to do the first one. The first one is actually the 35%. They use the 1 clock cycles. Then add to the 25% over here. Multiply 2 clock cycles. And then the 15% multiply the 2 clock cycles. Also last one, 25% multiply the 3 clock cycles, which is the branch. So if you do this operation using the calculator, so you will be able to get that for this program, okay, or for this program, you can actually get 1.9 per instructions, 1.9 clock cycles per instruction. So this is actually the answers, 1.9 clock cycles. You actually calculate this, okay, 1.9 clock cycles. So this is the first question. Okay, any question you want to ask me? Let's calculate yourself. Okay, if you have no questions, then we go to the second question. The second question is, from all these operations, we observe that 35% of the ALU ops, okay, so this is the first one, 35% of the ALU operations are basically they are paired with a load. Meaning what? Meaning that 35%, they, after add, they will have the load operations. So, okay, let's say that 35% are paired with a load. So 35% of this 35% is paired with a load. And then we propose to replace the ALU, this ALU operation and their load. Okay, let me tell you what is this. Let me explain a little bit further. I will turn on the whiteboard. Okay, what is this? This one means. Let's wait a while while my whiteboard is turning on. So you will have a add, after that you have a load instructions. So because this happens so frequently, so that's why they want to design a new computer which can have one operation that can handle these two instructions. Okay, now let me later show you. So in this case, with a new instruction, so the new instruction take one clock cycles. So it's very good. They combine these two, then they only take one clock cycle. So very, very good. Okay, but what is the problem behind? Yeah. Okay. The problem behind is with the new instruction added. Okay, because of this instruction added, the branch got problem already. When they need to branch, they need to have 5 clock cycles. They need to have the 5 clock cycles. Why is that happen? We don't know, but maybe because the architecture is more complex. Then when they draw a wire from this transistor to another transistor, it take longer path. That's why the branch may take more than 5 clock cycles. Okay, yeah. So let us my whiteboard still haven't turned on. Yeah, it come on. Okay, now let's see what is the meaning of this. Okay, they say that, okay, 35%. Let me wait. Let me wipe it first. Okay, they say that 35% of the ALU operation over here is ALU. It's like this. Okay, let me show you the example. Let's say add AL2. Okay, then after that, they will have the load instruction. Load, let's say load AL. For example, they have observed that this problem happens, this sequence happens for 35%. So they don't want this one because you see a clock cycle 1, clock cycle 2, clock cycle total, we have 3 clock cycles. So we don't want 3 clock cycles here. So the computer designer actually they want to use another instruction called add and load. Okay, add and load. So this instruction, maybe they just add and load. They create an AAL instruction. Okay, then you just run like this AAL2. Then you only take up 1 clock cycles. So they want to do this. So for 30% of the ALU operation, they can save the clock cycles. So this is what is meant by this. So but with the new instruction added, the branch takes 5 clock cycles. So in this case, we want to calculate the new CPI. Okay, new CPI. The new CPI will be equal to this. Because as you can see, the number of instructions that can be reduced is this one. Okay, 0.35, 35% of the 35%. You see, 35% is ALU operation, and 35% out of this 35% can be converted to another type of operation. So in this case, the new CPI equals to 0.35 minus the 0.1225. This is the original ALU operations that have been taken out. It's 12.25% has been taken out. So originally we have 35%, so now you take off 12.25. So you get this percentage multiply 1 plus 0.25. This one also the same load. Yeah, you can see the load operation there. 0.25. Also, they have taken out this 0.1225. So multiply the two. And then plus the original one, 15% multiplied 2, plus 12.25, plus 25% multiply 5. Now you have to take 5. After that, plus the new one, 0.1225 multiply 1. This is a new instruction. Then divided by 1 minus 0.1225. Some might ask me why we have this number lower. Anyone can tell me why we have this number lower? Okay, why? Why you have the 1 minus 0.1225? Because the number of instruction has been reduced. Yeah, this one has been reduced. Okay, so has been reduced. This one has been reduced because two instruction, add and load, has become one instruction. That's why the number of instruction has reduced. When number of instruction reduced, so the clock cycle per instruction also, and the denominator also reduced to 1 minus 0.1225. In this case, you will be able to find that the new CPI will be equals to 2.155 divided by 0.8775, which is, what is that? 2.455. Now let me ask you a question. Is the new CPI better or not better? The clock cycle per instruction better or not better? Anyone can answer me? Let me run a poll. Yeah, it's the new. Let me run a poll. Wait a while. Only yes and no only lah. So pretty easy. Yeah. So I will start a poll. Is the new computer has better clock per instruction? PTI. Answer 1, yes. The second answer, no. Okay, I'm going to launch this poll. Okay, so let's answer this within 2 minutes. Yeah. If you use the handphone, then you can answer me through the text box. Yeah, I see one word. Yeah, no. Yeah, very good. It's a big report. 3 words correct already. Yeah. Okay, very good. All have been able to answer, yeah? Or all done correctly, yeah? Very good. Yes. Okay, I'm going to end the poll in 5 seconds. 5, 4, 3, 2, oh. Chia Long Ho. Oh. He wants to enter outside. Okay lah, admit lah. Never mind. Just come in. Okay. So we are going to end the poll now. So very good. All answered correctly. Very good. Yeah. We have the higher clock cycle per instruction. But does that mean that our new computer is no good? Is that correct? If according to CPI, it's no good. But don't forget that the number of instruction has been reduced, right? You see, number of instruction has been reduced. The time might be different, right? So let's calculate. So now, let's say, but definitely 2.455 is definitely a lot higher, right? Clock cycles per instruction. But you can see that reduction 12% of the instruction. Then the clock cycle increased 50%. It's increased 50%. So it's not good, right? So third question. So if the clock of the old version is 20% faster than the new version, which version has faster CPU execution time and by how much percent? Okay, so They say that the clock of the old version is 20% faster than the new version. Okay, clock of the is 20% faster than the new version. Which version has the CPU execution time and by how much faster? Wow, this one. Okay, the new over the old is 1.2. If the clock of the old version is 20% faster than the new version, new over the old. Okay, clock cycles. Okay, so this one, the clock cycles time for the new one over the old one will be 1.2. Okay, so the new clock cycles time equals to 1.2 multiplied CCTO. So because you have already designed a new computer, right? So your clock cycles time has been increased. Because when you design inside, you have a lot of metal, all those wire, transistor. You design sophisticated one. So you can see that actually, when you do the place and route from one transistor to another, because the estate is larger, right? So you have to do the routing longer. So when your wire become longer, so when the electric need to move from one place to another place also take longer. So clock cycle time will be higher. So that means from the 2 gigahertz, you have to drop to 1.5 gigahertz if you design a more sophisticated one. So this is the problem. So you can see that this is the one. So the CPU execution time for the old one is 1.9, right? Originally, we have the 1.9. You can see here, we have 1.9 original clock cycle per instruction. Then we have the new one will be 2.455 or 2.46 here, approximation. So execution time here is 1.9 multiply the instruction count, which is 1, then multiply the CCTO, which is 1. Okay, then for the new one, the execution time equals to 87%, because it's at minus the instruction, right? And then you multiply the original instruction count. Okay, so 87% of the original instruction count, then multiply the 2.46. This will be the clock cycles per instruction. Then multiply 1.2. Now you have to use more time because 20% more for your new version. Then multiply the CCT. So you will get 2.59 multiply the ICO multiply CCTO. In this case, you can see that the old version is definitely better, faster by 1.36, which is 36%. So what happened to this new computer? Totally fail, right? Right, totally fail. Because you design a more sophisticated computer, then you take longer time, and then your program take longer time to run, and your computer need more time to design and more costs involved because more engineers need to go and design them, and then you come up with a slower computer. That's why don't do this kind of before you design any computer, you must do the performance analysis to make sure that when you design, put a new design, you don't actually slower down your computer, right? Yeah. Even though you find that, oh, okay, I can do a faster, you think I'm very smart, yeah. But at the end, you might get the wrong answer, the slower computer. Any question before I can continue? Chia, do you have any question or any other students?
So far, no.
So far, no. Okay, very good. So thank you, Chia. Okay, now we are going to do the last question. Okay, last question is question 7, which is last question. Yes, I heard the voice. No, okay, Hing Dong also say no. Okay, thank you. So the last question will be this one, question 7. Let's see. For the purpose of solving a given application problem, you benchmark a program on 2 computer systems. Okay, we will have you want to compare. Benchmark means you sit at the chair there and then you mark which one better, like that, benchmark one by one. Okay, so a program on 2 computer systems. On system A, the object actually typically execute 80 million ALU operations, arithmetic logic unit operation, and 40 million load instructions, okay, and then 25 million branch instructions. So these are the three types of instruction. Then on the system B, the object code executed 50 million ALU operations, 50 million lots, and 40 million branch instructions. In both systems, each ALU operation take 1 clock cycles. So ALU is the fastest one, and then each load take 3 clock cycles because it involves memory access. This one just involves the transistor, and then each branch take 5 clock cycles because you need to branch. You have to increase the PC, and also you have to take the new instruction 2 times, right? So even slower, right? For load, you just load and then come to the register. But for the branch, you need to increase the PC, okay, program counter, then program counter go to memory, fetch the instruction, come back. So this one will be longer, okay, as what we learned inside the micro instruction and micro operation, right? You have to have a lot of control signals there. So the ALU definitely is faster because it's just within inside the IC, right? A portion, very small portion there, all the transistors are inside there, right? But for the load memory, right, you have to go to the whole wire and go up, go to a RAM. Okay, so this will take you a lot of times. So now, compute the relative frequency of the occurrence of each type of instructions executed in both systems. Okay, you can see that this will be they want to compute the relative frequency of the occurrence. Okay, what is the relative frequency? What is this relative frequency? Okay, what is this? Relative frequency? Relative frequency means the frequency compared to the total frequency. Okay, so this is called the relative frequency. So you can see here, okay, we have the A and B. For the ALU operation, you see for the first one, we have 145 million, total 80, 40, 25 million. So it's 145. On the system B, we have 50, 50, 40. It will be 140. That's why you have the denominator as 140 here, and the denominator is 145 here. So the relative frequency will be 80 divided by 145. Here is a 50 divided by 140. So the next one, for the load, 40 divided by 145, and for the B, the load is 50 divided by 140. So, and we calculate for the branch as well. So you will get 55% for the AA goes to ALU, 28% go to load, and the remaining 17% go to branches. Okay, for the B, 36% go to ALU, and 36% go to the load, also 28% go to the branches. So this will be the percentage of different instructions, okay, for the system A and system B. Okay, now we answer the first question. Any question you have for the first? You can take 2 minutes to look at this. Okay, and if no question, then I better go forward here. Okay, fine. Let me check whether there is any question. No question. Yeah, got one question. Let's see here. What's the question? Disappeared. Yeah, disappeared already. Oh, no question. They say, okay, never mind. Okay, Hindong, no question. So now, let's continue. Find the CPI for each system. How do we find the CPI? So you have to, in both systems, each ALU take 1, load take 2 CC, and the branch take 5 CC. So you have to multiply. So for CPI clock cycles per instruction for the system A, it will be 55%, multiply 1 clock cycles, plus 28%, multiply 3 clock cycles, and for the branch operation, it takes 5 clock cycles. Eventually, you get 2.24. But for the system number B, 36% multiply 1, 36% multiply 2, and then 28% multiply the 5 clock cycles for the branch. Branch has a higher number of clock cycles. So if you calculated this, so you get 2.84. Yeah. So now, last one. Assuming that the clock on the system B is 10% faster than the clock on system A. So you have system B and is 10% faster. What does it mean? The clock faster for the B. So which system is faster now? For the question here, which one is faster? Let me. Oh, never mind. This one is too simple. I don't want to ask. So system A faster, right? Because it has 2.24. But system B, you take 2.84 per instructions. Okay, now, last one. Okay, if the clock cycle is faster, so which one is faster? Okay, so let's say B is 10% faster. Now we want to see B is faster 10%. So we go and use this formula. So the CCT clock cycle time per A per B equals to 1.11. Mean the time for A is higher by 10%. And then CCTA equals to 1.1 multiplied CCTB. So as such, the CPU execution time A equals to 1.145 multiplied 10 to a power of 6 multiplied 2.24 multiplied 1.1. So you can see 1.1 over here. Okay. So you can see that if you calculate it like this, so you should get 3.357 million. Okay, of the CCTV. Okay, so now let's look at this. If you calculate it for the B, so it will be 140 instruction million instruction multiplied 2.84. Okay, but the CCT of the B is 1. Here is 1.1. Okay, now you get a 397.6 million CCTV. So comparing these two, so which one is faster? Let me ask you a question. Let me run the pool. Yeah, I do want to show you the answer first. Okay, assuming that the CPU execution time for CPU A execution time is 357 and CPU B is 397. Okay, time. So which one is faster accordingly? So let me run a pool. Yeah, I will run the pool over here. Okay, which processor is faster? Okay, I see here answer already, but don't worry. Still we do the pool. Yeah, it's faster in terms of CCT. Okay, answer is A and B. A and B. Okay. Yeah, I'm going to launch this. So yeah, let's answer this within 2 minutes. Now, which one is faster? See, this one. Which one is faster? Is that overturn the winner? No, right? Okay, let's see. Yeah, I'm going to end this in half a minute. Okay, 8 votes already there. Okay, 9. Yeah, all answer A. Yeah. Let's see whether the answer is correct. Yeah. Okay, I'm going to end the pool. 5, 4, 3, 2, 1. All answer already. Okay. Yeah, last minute answer. Okay, very good. So the answer is A. Yeah, very good. Let's give a big round of applause to everyone. So the A is faster by 11%. So by 11% because you compare the time given by the needed by system A and B. Okay, so you get the 11% different. Okay, so yeah, so I have finished this. I've also uploaded the answer to you to the Google Classroom. Yeah, so you can have a look at this. I will also upload the video for today, so you can have a look at this. If let's say you are eating your reunion lunch when you study these lectures, so you can still do some revision. So thank you very much. So any question you have before we end our class today? And I want to wish everyone happy Chinese New Year. Okay, all the best, and see you next week. So hope you keep safe and don't go out so often. Okay. Any question? Okay, if no question, then you are allowed to leave. Yeah. So thank you very much. Yeah. Thank you very much, Chie and everyone here. And also Heng Dong. Yeah. You may leave the class. So thank you. Happy CNY. Okay. Bye bye. Bye bye. Okay. Thank you.